Hi everyone, good morning. Um, Welcome you to the Godment School. This is the fourth lecture of our series Motifs in Algebraic Geometry, and we have Professor Umesh Dubey from HRI as a speaker for this lecture. This lecture is entitled Injective Sheaves and Constructions of Sheaf Cohomologies.
Okay.
Yeah.
Yeah. Thank you once again. So I'll just share the screen. Okay. So is this visible to everyone? So let me begin. So in last lecture, we started introducing sheaf cohomology, and sheaf. So we recall sheaf, pre-sheaf, and sheaf, etc. So which was defined as a functor, and then we defined certain sheaf condition, and there was a stop functor, global section, and then we said there are certain property, like if you specialize to category of sheaf of abelian group, which you called abelian sheaf. So this was our notation. And finally, last time we also gave some example, and we indicated like some of this extra property of abelian category which holds in this for this category of sheaves of abelian group, or more generally sheaf of OX module. And in a sense, this was a motivation for him to kind of unify this R module category, abelian category, which has nice property, and this sheaf of module category. And that unification now we call something like grothendieck abelian category. So this, if you remember, we had this axiom AB5, which says that AB3 holds, meaning there are arbitrary coproduct, and there is a generator in this category. So, and eventually we showed that this category also has similar property. So this property here, AB3 star, is a general consequence of this grothendieck abelian category. So it is already follows from there, some representability argument. Let me just quickly say what was the grothendieck abelian category, since it's very interesting. So the condition what we let me just quickly recall what was this AB5. So first AB3 was there, which says that this direct sum exists. And as you see that all set theoretic arbitrary direct co-limit here, this will be also equivalent to, because of that quotient is there, this is abelian category, you can prove that this all co-limits exist in this category. So sometime you see this is written like this also. So these two are equivalent here again, and the dual notion is that you replace this by direct product or limits here exist, and then AB4 we last stated in as saying that this direct sum, if you think of it as a functor, this is exact. It's already right exact, so only thing is that this is left exact, which was equivalent to equivalently saying that direct sum of monomorphism is a monomorphism. And finally, there was in terms of some this yeah, here this is assumed, so this is AB3 plus this. Similarly, like this should exist plus this is exact. Here also you say AB3 plus some very specific type of so let me just say last time it was in terms of some sub-object and this some distribute over like with respect to infimum or something, which can equivalently written as filtered colimit is exact. So here, this filtered colimit here means that this generally, like when we define limit or colimit, this is defined for a functor which is from some index category here, I. So you want that this index category should be filtered, meaning it should have, I mean, first of all, non-empty, and there are given any object I and j, there should be k which is bigger than both I and j, and given two parallel arrow, there is co-equalizer. So there should be a case as that. So I and j with u and v, there should exist w such that wu is equal to wv. So in a sense, this generalizes all those directed set etc property. And so this category I is filtered if this property holds. So, and if I is filtered, then this colimit you call filtered colimit. Yeah. Assuming non-empty here, and this property here, this two property here. Okay, so there are these equivalent ways of formulating this. And so similarly, the dual you will have to write something like co-filtered limit exists. So this co-filtered index category, on that you will take a limit and then you say that that is exact. Okay, and then additionally there was a generator which was defined as last time. And since AB3 is there, in place of family you can have a generator. So you can write one generator such that whenever you have like sub-object here, proper sub-object here, there should exist a map such that it does not factor through this. So there does not factor through this. So such a factorization does not exist. So given B, there should exist some, let's say phi B or something. So in a sense, from here you can see that each sub-object here is like there exists some morphism here, kind of. you can say that this gives a map here of, because morphism is by our definition is a set. So from here you also see that sub-object is forms a set. So there are some other consequence, but let me not go into that. So this is a generator. Whose existence is part of this definition of Grothendieck abelian category. And as example, as I said, that R module, you can take R. In this abelian category of mod R. Now here, what happens is that in this particular category, example mod OX, there are this example, what is called OU, which is you define so let me so you define it 0 if V is not contained in U, and otherwise you just define as it is, like OX of. Now here, what happens is that any question? Sorry. OX. There are this example what is called OU, which is you define as the OX module. So let me, so we define it 0 if V is not contained in U, and otherwise. So on U it agree, on U it agrees with OX, whatever the definition. Any question? U is open, or U is open here, I have taken. Yeah, here U I am taking is open. As a OX module. As a OX module, yeah. So this is an object here. So on U it agrees with OX, whatever the definition. Yes. Right, right. And on outside it is 0, yeah. Right. It's open here, I have taken. Right. So this collection of objects, you take direct sum, so that will be the corresponding U for you. Like you run over all open set and consider OU, direct sum of all. That will be generated. An object here. Sorry. Voice was not at all clear. I don't know. So if I take this is a generator, is what I want to say. Is this statement clear? Okay, so the point is that what you have to observe is that this home, when you are considering this home sheaf of, I mean, I'm saying in this category, from this to any sheaf, you can identify this with FU. Once you observe this, so now it is easy to see, like if you have any subobject, proper subobject, then there will be U on which it won't agree. So therefore, given that element which is not inside F prime U, you can take that corresponding morphism and you will see that it won't factor through that. So from this observation, you can just prove this. Yeah, somehow, yeah, there was a question, but I could not get. Maybe towards end we can try to clarify. Okay, let me just go ahead. So this was we did last time. I was trying to recall a few things, and a few things we did, like some of these things, and then there is this other construction which will prove for this there is a generator. Now next aim, what we wanted to see is that if you consider this category mod OX or abelian sheaf category, this has enough injective objects. So you can embed in every sheaf into some injective sheaf. And secondly, you can do it functorially also. So that was the two main aim where we are heading now. So let's see. Yeah, so first of all, as I said last time, you can define injective sheaf or injective sheaf of module here as an injective object in this category. So this means that you call it injective sheaf. Let me just abbreviate like this. If this hom dash I is exact. And since this is the left exact functor, so this is becomes equivalent to saying that whenever you have a sheaf and a morphism to I, there exists an extension. So this is clear because this is already left exact. So only thing fails is that lifting from here. So if you write down the short exact sequence f prime f double prime, so you will immediately see that this is equivalent to this. So for each u there should exist this, and yeah. So the statement is that there exists u tilde. So for all such sequences. There exists. So this is the another equivalent way of saying this is the injective sheaf. And there is a more general fact for the Grothendieck abelian category, which is there in the Tohoku paper. Let me just recall that fact. So which is that it is enough to look at this existence property. It is enough to do it for the subsheaf of U. So it is enough, like you can take in Grothendieck abelian category. Let me not. Okay. So this is for this particular abelian category. I is injective. If this extension happens for all sub-object of the generator. So if you take this generator and if there is extension, if there is a map, sorry, this is the map U, and then there exists, let's say U tilde. So it says that I is injective if and only if it has this property that for all U and such a sub-object of U, there should exist a extension of this morphism from sub-object to the whole thing. Okay, let me not write it. That's just to save time. So it should be clear that, I mean, here we are demanding for all inclusion, but now in this Grothendieck abelian category, it simplifies to only asking for this sub-object of generators, all this inclusion. In particular, like, I mean, as I said, R module categories, this is like, you may already know, like, you have an ideal of a ring, and if there is extension from ideal to the ring, then that module is injective. So that it's enough to check extension for just an ideal included in a ring like that. So yeah, this is in from Tohoku. So I mean some more fact he does. So from this gives an injective, some way of checking injectivity, right? And just let me mention few example. As I said, for are there any questions? Okay. So yeah, somehow I can't hear properly. Is there a question? Okay, some noise. So now, as I said, mod OX already, if you consider some example, like, I mean, if you are interested in mod R, for example, here you already know how to get injective object. So you are familiar with here. So some of those construction which we will use here. So from our module, this construction of injective, we want to construct, give something for the injective sheaf. I mean, we want to construct something injective sheaf, right? So like for example, here, let me mention one example at least for R. What you do is this, what is called R dual. R check here, this is defined as home disabling. So this you check is that has a R module structure. So I leave it for you to check that this is the injective R module. Yeah, for abelian group, there are characterization which says that something is injective if and only if it is divisible. And from there you check Q mod Z is injective, and then from such a injective object, you can cook up something injective here. And now we will use these constructions for the safe case, that is the aim, and that example which I have mentioned earlier, which I think essentially due to Godement. And right. So now, first of all, there is this construction of a skyscraper sheaf. So what you can do is that fix some point in X. So you can fix any value also with value, let's say, let me say Ix. So what is this sheaf here? Okay, to should not conflict with the notation earlier. So this is, let me just say, this is the notation. Let me just ignore this part here. This some value here. So this is the skyscraper sheaf. You define this to be this particular I whenever X lies in this V. Otherwise, you declare it to be 0. So this is the skyscraper sheaf. So now what you can see is that, so what you can check, okay, is that if I is injective, so somewhere I have to write, let me write here. module. Then if you do this construction, then this Ix becomes injective sheaf. Okay, so to see this, what you have to observe is that somehow there is a more general adjunction, or you can just prove directly that for any sheaf, if you do this stock here at X and this I, this is isomorphic to F, this Ix. I hope this is visible. So once you prove this identity here, which is if you are familiar with adjunction, so this is like saying that this Ix lower star for inclusion of a point, this top functor is a left adjoint. So so proving such a statement here, and you already know that this is exact because top functor here is exact, and then you're taking home with this injective object here because this is injective as a OXX module. You prove that this functor here will become exact, and therefore this is injective. Okay, I hope that argument is clear. So Ix is injective is equivalent to saying this hom dash Ix is exact, and that is exact because of this observation that this hom agrees with this hom fxi, and this is exact, this left side functor. So therefore you immediately starting, so okay, so the starting with injective module over this local ring, this stock over this stock, you can do this skyscraper construction and get an injective sheaf over whole topological space X. Okay. And the next observation, what I am saying here is that so this is one type of construction, like starting with some injective object, you are constructing injective object in this category of sheaf. Now the product, again, you observe that product, if you take hom from any sheaf to, let's say, product or any arbitrary this indexing, so Ik, there's nothing but this product, this coincide with it. I mean, you can see from universal property of product also that this is agrees with this. So if you have so if suppose there is a such a data that f prime to f is given to you, so think of this situation here. So what you want to prove is that suppose f prime you are given there is this product Ik here, and then this hom here has agreed with product of map from f prime to Ik, but Ik is injective for each k we have assumed. Then what happens is that then for each you will have u tilde k, that extension, and then again going back to that identification, you will get hom from f to this product Ik. So it's like product of u tilde k if uk is that map here. So you can easily check that this fact here, that product of injective sheaf that remains injective. Any questions so far? Okay, so basically what we have done is that in this category of sheaf of abelian group or sheaf of OX module, first we can do this skyscraper construction to get a injective sheaf, and then now we have proved that product is also injective. So you take product over all So from here, you will immediately see that if you run this product over all points of X and look at this Ix, so that is injective. So basically, what you can see is that okay. So this is your this product is running over all the points here. So you can see that this is injective sheaf. Okay, so and now you can observe that this is nothing but that definition which I have given earlier of this particular sheaf, where you send your U to this product over of course here I mean I can vary this I also with respect to X, so somehow it's not completely clear from this construction, but I could vary my X also. Okay, so somehow if I could subscript just to say that this injective object is also running over that. So so this was that construction of sheaf we have given earlier. So this particular sheaf where you define for each open set U, you take that some OXX module, which is that IX, and you just take this X belong to you. And what is the restriction is just you take the just project onto that whatever that factor which is coming from this U to V restriction. Okay, so this particular sheaf it agrees. So this can be described in terms of this. So what you see is that this particular sheaf here is injective.
Excuse me, sir.
Yeah.
Yes, sir. So here I skyscraper sheaf at X is just a.
Okay, so here I just took this notation, meaning this is that at each point you are taking this particular module and you are doing the skyscraper.
Oh, okay.
Upper script was denoted as a skyscraper. Here, this is the okay. Somehow maybe not a good notation. So here, this was the definition. That skyscraper with value I, but I can take with value IX also, just to mention that it is.
So sir, first we are taking stock and then skyscraper sheaf of that, right, sir?
Yeah. You
is
can
it the same?
No. So there is a two thing. What you are referring is that I start with F, and I have this stock X Fx. I can define this also as my example. This is also an example. This is an example maybe I would have given earlier. So this particular sheaf you are taking only stock. But what I'm saying is that in place of Fx, I could have taken any OXX module. If let's say Mx is a OXX module, then I could have taken this particular sheaf where you just take that particular Mx. These are all example of this sheaf, because naturally they will have OX module structure because there is this corresponding map. You can just check that this has the module structure, OX module structure. Checking sheaf of abelian group is easy, but even you can check there is a module structure. And this particular, this second construction, what I'm saying is that this, if I take in place of Mx some injective OXX module, then this construction, these two agree. It will agree with the skyscraper sheaf with value that same Ix. or this could have said for mx also, but doesn't matter. Ultimately, this fact here, which is a product of injective sheaf is injective, is to proves that this particular sheaf is injective. Yeah, you can say this kind of construction is due to Godement. In fact, he calls it a special name, which we say like flask sheaf, meaning flask sheaf is one where all restriction maps are surjective. So these from here, you can easily see that these are all projections. So these are all restriction maps are surjective. So this is what he has studied, something called flask sheaf. And yeah, these are all example. And what we are further, yeah, any question? Sorry, not here.
Shruti, do you have a question?
Okay.
No.
Okay, so I hope so. This gives some example of injective sheaves. So, right now, so as I said, you can given any sheaf F here, you can do this construction. And let me just call this very specific sheaf to be F tilde or something, some ad hoc notation. Yeah, so this F tilde here, you see, has a very nice property. In fact, this F is embedded in F tilde. And that's how maybe we will use this to construct our injective, this embedding. So let me just go to the next page. So these are all construction due to Godement. I think it's there in his book, and he constructed various example. And also this construction, you can see here, it gives example of injective object. Right, so just let me note here this observation that you can define easily, there is a map from F to F tilde, this particular F tilde using the stock, and there is an injective map here. This is in fact an injective. You can calculate the stock and then you just check that this is injective here. So there is a canonical injection here you can do from F to F tilde. In fact, this is also functorial. If you see, this is if we have to G, then there is F tilde to G tilde. This is that functorial embedding or canonical embedding. Of any sheaf into a flask sheaf. If I say what I just said, a flask sheaf is or flabby. Sheaf is the one where this restriction Fu to Fp is surjective. So if such a thing happens for all here, then you call it a flask sheaf. Okay, I'm not writing in detail. So, but from an example is this F tilde. And what you have shown is that there is every sheaf is embedded in flask sheaf. I don't know if it is pronounced that way. This is some French word, or flabby, you can say. Yeah. Okay, so now we will use this embedding here to go further in some functorial way, embedding in some injective sheaf. And so we have all the ingredient here now. So what now we have to observe is that how do you get like this embedding? So for this, we need to do this, what I said, that tilde construction. So basically the claim is, okay, just to mention two facts here before I go to that embedding result, is that first of all, you can observe that you take any injective sheaf and you restrict to that open set. So you will get OU sheaf, and that is again remain injective. And if you again the proof is you have to just say that use that definition and try to prove this. I guess just observe some fact about home. And similarly, of course, this is true only for open, not true in general. And the second construction you can do is that if you have something extending by 0, if you have closed sub here, so this is the closed sub inside X. And if you got any sheaf over Y which is already injective, so J is injective over Y, then if you extend by 0 to the whole thing, which is also, I mean, you can also think of this way. So I just wrote, maybe it's confusing, but something like you are pushing forward from this closed immersion or something. So this is the sheaf, like as we defined that skyscraper. So this is more general, from any closed subset to X you can define extension by 0. That particular sheaf is also injective. So again, you have to compute the Hom, some exactness of Hom that should follow from this identity here. Okay, this I will not go into the proof, but these are two additional construction of injective sheaf. You can see starting from injective sheaf of X, you can get injective sheaf on this open U. And starting from injective sheaf over this Y, for example, what we did for the point, you can get an injective sheaf on whole of X. This kind of skies. So this is a more general version of that skyscraper construction which we did. Like when you have Y equal to X, you are getting that skyscraper. Okay. So yeah, so finally, the first aim, what I was trying to say is that how do you get functorial embedding of this sheaf? So you started with a sheaf. So as I said, you can, so first observation is that given any module, let's say there is a functorial way of embedding this into. So there is a functor which embeds these two. I mean, in fact, is a functor plus there is a morphism also, and which gives an embedding. Sorry. Yeah, so this embedding here. So first of all, we prove this for module and then eventually use this construction to the sheaf case by that usual skyscraper, this that flask sheaf construction F tilde. So we'll combine those two constructions. So first of all, how do you do it for module? So what you do is that you take so first of all, recall that I defined this M check as Hom M Q mod Z. Okay, take this M check as a set, and if let's say phi is this element in M check, you generate a free R module by this element phi. So take this free R module and then take the dual. Then again take the check. So basically this is R check. I mean, this just to keep track of the index. So this particular one, so first thing you can observe is that, so let me first for the module case. So first thing you can observe that JM is injective R module. Why is that? Because this is just a product of R check, and R check is already, we have observed that this is injective R modules, and the product of injective is injective. So therefore, the JM becomes injective. And in a sense, what this map here comes from this. First of all, there is this, if you do denote by this whole, this complicated product as some kind of free module generated by M tilde or something. So as a set M tilde, you can generate free R module denoted by F M tilde or something. So this is, this particular thing we have written is M check here. So this is nothing but whole chain. So f of M check is nothing but R phi, this phi running in M check, and this has a P from these two M check by construction. And therefore, when you do this check construction here, which is an exact functor because this was injective already, so that will reverse this surjection to the injection, and what you get is that injective map from this to which is what we are denoting by JM. And this M2 already you have a evaluation type of map, meaning this M check, any element here going to this evaluation. So there is a canonical map here. So you compose this. So this is that injective map which you get here. Okay, so basically what we have achieved is that given any module, you have this functorial embedding in some injective module. So now use this fact so how do you do it for sheaf? So what you do is that you start with a sheaf, and you have this embedding into this F tilde, which was the, I mean, you can say over U, it is a product of all the stocks. And what you can do from here, you can now define this new sheaf. Let me just write it as a sheaf. So this sheaf is defined as over U, you just send it to product of J, this J construction as a OXX ring. This is for FX. So this is the stock. You take the stock, you embed that stock. So you do this J construction in this category. So if I more precisely say this is happening in the, for the ring R. So this is the J for this particular ring, local ring. And then of course, product running over whatever you. So this particular construction here, now you can see that this stock here is this fx, and this is, or fx is already embedded in J of fx. This composite here gives the embedding into like this sheaf, like J tilde of it. So this is the functorial construction, I mean, of this Godement, or sometimes called this embedding here. So that is, you first go to F tilde, and then from F tilde, you each stock level, you use this functorial embedding into some injective module, injective OXX module, and then just discompose. So basically what you're doing is that each stock level, you are getting an injective, I mean, embedding into some injective, some canonical way of doing it, which is becomes functorial. I mean, you could have done any embedding, but that, yeah, may give some injective sheaf, but using this check construction, whatever, you're making that construction little more functorial. That's the advantage here. So this gives a functorial embedding. Okay. So now, once you have such an embedding, it is easy to get the resolution. What you do is that you just embed and then take the quotient sheaf, again get an embedding, and I mean, you might have done this many times. So what you do is that you started with F, and then you did this construction for J tilde F, and this is what is your I0 or something. And then you take the quotient. Let me just say F1 is the quotient. And then you again embed this into by the similar construction here, and then take this composite. And now take this map, and here you define F2 as the quotient, and you keep going like this. What you get is that you get the resolution of injective here. Okay, sorry. Okay, so this is what you're calling this injective resolution here. And as I mentioned earlier, once you got the injective resolution, you immediately, you can get the right derived functor of any left exact functor, in particular global section functor, etc. Now, as I said, there is some result in the Tohoku paper. If you see that many times you need not have to take injective resolution to get this result. Sometimes F acyclic is enough, and these are easier to get than the injective resolution, etc., meaning easier to handle. And so by what is the definition? So you call it F acyclic if this higher derived functor, this is 0. In particular, when you are taking this gamma functor, what you are saying is that gamma acyclic means that if this HP X K, this sheaf K, this is 0. So all higher sheaf cohomology vanish for that particular sheaf, then you call it gamma acyclic. So then what happens is that once you get embedding of your sheaf into some acyclic, some acyclic resolution, let me say F acyclic resolution, which means that similar such sequence where all objects are F acyclic. Here all objects, so again, I'm not defining resolution, but you must be familiar. So resolution here, injective resolution means that each term here is injective, and then there is exactness, and only at the 0th level this kernel is this F. So this as a augmented, this is exact. So then you call it a resolution, injective resolution if each term is injective. Similarly, you call it F acyclic resolution if each term is F acyclic. And the point is that once you have F acyclic resolution, the result says that the right derived functor can be computed in terms of f acyclic resolution. So this right derived functor, so if I'm not stating the full generality, etc., but it says that if k dot is f acyclic resolution, let me just say for gamma, maybe you can make out what is that mean. Gamma acyclic resolution, then your HIX k dot is gamma x resolution of, let's say, f, then HIXF, this will agree with homology of gamma k dot. Yeah. And example is, as you can see, that flabby sieve or flask. Flash sheaves are gamma acyclic. Or sometimes you say it is adopted to this particular content. Yeah. So this fact could be proved, I mean, in few steps. There is a more general axiomatic way he proves by defining suitable class of object in Tohoku paper, and which roughly says that some collection of object which is closed under Saman retraction, and it has certain exactness property with respect to flask sheaf. Then injective object sits inside this, so injective object become flask. Okay, so that maybe that fact maybe you can observe here immediately, that injective sheaf is flask. Yeah, so again, this is like you just have to observe that there you get the submodule inside OX, and observe that this morphism is nothing but IU, or let me just say that not whole X, but even so such a extension will follow, I mean, which is like it says meaning you want to show that if whenever U is contained in W, then IW to IU, this is surjection, which I am saying can be equivalently formulated in terms of this morphism from OU, and then extension is like saying that this extends. Yeah, I just leave it for you to check that this property here, injective, will prove that it is a flask. There are other type of sheaves which are also for very specific topological spaces like paracompact, etc. What he defines soft sieve, and they become flabby, and therefore they could be used. Now, basically, what I wanted to say, yeah. So this is all about that injective resolution, and therefore we have sheaf homology definition, etc. And There is a more general result which says basically once you have f acyclic and some property, then like you have to here I just stated that this will agree with the Sheaf cohomology, but essentially he has formulated this everything in terms of universal delta functor. So under certain condition, these become universal delta functor, the collection of functors. And therefore, by universal property, you get equality. So many times this proving something agrees is going via showing that this satisfy that property of the proposition, which will say that this is a universal delta functor and therefore they exist. So this is a common technique here, like you always have to prove something is universal delta, then by universal property they coincide. And yeah, there is a slight variant here which I wanted to say, like here we said about the gamma, but you can define something called gamma phi, the slight variant. So what is phi here? So let me just recall what is the phi here. Just a second. Yeah, so what he calls this phi, something called increasing filter of closed. So there is some assumption on this. So this phi is a collection of closed subsets of X. So what we call increasing filter of closed subsets of X. Such that, I mean, if A is in phi, then all the subsets and B is containing A is closed subset. So they should lie in this B, lie in this phi. So it's here filter means this. So this collection of closed subset, this is like whenever there is a closed subset contained in that closed subset, that should also lie in this. So that is the property you need here. And so then if you take such a collection, then gamma phi, which is defined as a sub of gamma. So basically gamma phi with respect to this phi, gamma phi of f. This is a collection of all that section. So as I said, we refer to this as a section. This is an element here, says that outside this phi, this support of S, this section you can define that complement of that largest open set where this S is 0. This should be inside phi. So this should lie inside this. So collect all those sections which has this property. So this will be sitting inside yeah, gamma F. So this slight variant here, what you can prove is that like here gamma you know already. I mean this also you can identify as home X F. This is already left exact. I mean this gamma is left exact.
Professor, we are slightly out of time. You may. Yeah.
Okay, sorry. So yeah, so let me just finish by this statement. So maybe you can try to prove it, is that gamma phi is also a left exact functor. And therefore, whatever we have done so far, that any F is a has an injective resolution. So therefore, you can define this HI. So with phi support here with this extra support condition. So this now I can define as a right derived functor of this particular functor gamma phi, which is nothing but hi of you apply gamma this functor on the injective resolution. Let me just use okay J also. You can take J dot. So like in the case of gamma, you can write down this, and this is the gives a variant of that sheaf cohomology which we had. And there are you can study what are the acyclic here in this case, like flabby. There are some variant of this flabby or soft, the sheaf here, and you can get a resolution. So Godement has studied that flask resolution and to define his sheaf cohomology. But as I said, once it is F-acyclic, you can take any F-acyclic resolution to define the same right derived functor, in particular sheaf cohomology. Okay, maybe I'll stop here.
Okay. So thank you everyone for being here for this long 1 hour. And thank you, Professor, for this beautiful lecture. The closing of now, we'll meet next week at the same time, maybe.
Yeah, actually, I'll have to, maybe I am little busy next week.
Right.
Some conference. So
oh yeah, I know.
we'll decide.
Yeah, hold on a minute. I'll just stop the stream. Just hold on.
Sure.